Okay, so we'll start off this one by thinking about our apparent power supplied to the motor, which of course is this. And so our equation, S three-phase, is equal to root 3 times V line times I line. We've been given a measured value for I line. If we had a measured value for V line, we would use it, but the rated value is good. So root 3, our V line, 4 kV or 4,000 volts. And our measured current, 320 amps, gives us S. Three-phase is equal to 2,217 kVA. Now we could of course write that as 2.217 MVA or 2.22 MVA, I suppose. In any event, I wrote it as 2,217 kVA. Now part B is the power factor. And so remember that here again, no mention of a DC input to the rotor. But of course, if it absorbs 2,000 kilowatts from the line, that's our AC power in. And again, you know, that's probably a measured value from a watt meter. And so our power factor then, the AC power in, and you know, in this case, we're not given a DC source or any information about it. We can just call that P in like we've done for our other calculations. Over, and I should be putting this three-phase down there. And so we have 2,000 kilowatts over 2,217 kVA, so our K's cancel. And so now our power factor then is from that equal to 0.902. And normally when we calculate a power factor, we're supposed to specify if it's leading or lagging. Can we do that here? And you know, the reality is that we don't know. It's a boner. We'll assume that is lagging. But we don't really know if it's lagging because we're not told if it's underexcited or overexcited. If it's an induction motor, we can assume lagging, right? Because we know it's lagging. For a synchronous motor, unless we're told otherwise, we'll assume that is lagging because, you know, that's what makes the most sense, right? Now, part C, the amount of reactive power required to produce the stator's magnetic field. Okay, so there's another hint that is probably lagging. And you know, right now, remember that some of the stator's magnetic field or the flux produced in the machine is done so by the rotor. And so when it says, you know, phrased like that, the amount of reactive power required to produce these stator's rotating magnetic field, that's right now at that 0.9 lagging power factor. And you know, one of the things we described about the synchronous motor is that its most optimum operating point might be at a power factor of unity. From a point of view of drawn reactive power from the system, a 0.9 power factor is what is commercially acceptable. And so this machine is adjusted probably to 0.9. And so right now, under that circumstance, how much reactive power is required to produce the stator's rotating magnetic field. And so again, reactive power, of course, is Q. And so we're looking for Q. And we won't call it L, but we believe that, of course, that it is. The square root then of S 3-phase squared, subtract our AC power in squared, which I'm just going to call power in squared. And again, you know, I'm not going to put the K under the root sign, but we know that we got to include it in our Q. So 2217 squared, subtract 2000 squared. And when we do the math on that, we'll come up with Q is equal to, if I round it to three significant figures, 957. And so remember, there's a K in your unit, so kVAR. Part D, the number of poles on the rotor. And so what do we know about rotor poles? Well, we're told that because the magnetic field on the rotor must have the same shape as the three-phase field on the stator, then the rotor poles is equal to P. And remember, P is the poles per phase on the stator. And so even though the rotor field is DC, which kind of makes it seem like one phase, I suppose, it has the same shape. And so the rotor poles must be P. And so P is the number that we're trying to calculate. And you got to know that, I guess, which is why I asked for rotor poles there. Now, where's that come from? It comes from NS is equal to 120 F over P. And so from that equation then, poles per phase is equal to 120 times F divided by NS. And again, our 120 times 60 hertz gives us 7,200 in the numerator there. And our sync speed was given as 225. Now, it didn't specifically say that, but it's a synchronous motor. So we know that the speed we're given is assumed to be a running speed, but in this case, the sync speed as well. And so 7,200 divided by 225. And it should be a nice whole round number because remember, poles occur in north-south pairs. And so 32 is the result. And so 32 poles per phase. And of course, the reality is that means that that's on the stator. But the answer to the question then, of course, is that that means there is also 32 poles on the rotor. Okay, so the last thing then that we're asked to do there, well, actually there's two things, I guess, is find the output power in horsepower and the torque in Newton meters. And you'll notice that, again, I did not ask for torque developed, and that's because we don't know enough to come up with a value for mechanical power developed by the rotor system. And so we are given our efficiency as 92.5%. And this time we're working the other way, right? We're trying to find power out from that. And so if we know the power in value, we can say that power out, remembering of course that it's less than the power in, is equal to the efficiency multiplied by the power in. And so as a decimal, 0.925 and multiplied by the 2000 kilowatts that we had for power in. And so we can say then that the power out is equal to 1850 kilowatts, but we were asked to express that in terms of horsepower, and so times 1 horsepower divided by, with respect to units there, 0.746 kilowatts, and so kilowatts cancels with kilowatts. 1850 divided by 0.746 says 2480 horsepower. And so, you know, if our solution comes up with 24,080, we probably don't find that exact value on the nameplate because they put nice old round numbers on the nameplate, right? And so I suspect that what you find on the nameplate probably be 2500 horsepower, right? So approximately equal to 2500 horsepower, let's say that. Okay, so now the torque, and so remember again that it's a torque output, and we'll say that that comes from the 9.55 times P out, because that's the value that we have, divided by NS. So 9.55 then times, remember this value is kilowatts, so 1850 kilowatts, and so a lot of torque because this thing is a slow mover as well, right? 225 RPMs. And so if we do that calculation, we came up with 78.5, and because of the kilowatts, that's kilonewton meters. And that is output torque basically at rated load.